In the last video, I mentioned a transition state or an activated complex that you get when you've got molecules that collide and they temporarily are kind of stuck together as one piece until they get all their electrons rearranged and then they separate. Sometimes what happens is that it is so difficult for two things to react together that they actually have to go about it a different way. And that's called a reaction mechanism, which if you recall, I said that that's one way that a catalyst will work, is it can change the reaction mechanism. Well, today we're going to talk about reaction mechanisms. We actually also discussed reaction mechanisms when we were talking about Hess's law much earlier in the year. So this probably won't be completely new for you. Let's say that this is the overall reaction under discussion. Well, if you look at this, you can see that what has to happen is that I have to have not just two molecules that have to collide with the same energy or with a sufficient energy to overcome their electron repulsions and to have the proper orientation, but I also have to have an additional one. And so now I have to have three molecules that have to all collide together at the same time with enough energy in the right orientation in order to rearrange themselves. The chances of that are not very great. And so sometimes these reactions occur by a series of different steps. And so maybe I have just an A and one B that react together to make a C. Then C turns around and reacts with another B to make D. And then once D is there, it splits apart into E and F, and then I get my final products. So just like we did in Hess's law, if you were given only the reaction mechanism and you were asked what the products were, you would look at that the same way that we did the Hess's law problems. You can say, well, I have a C on both sides and I have a D on both sides, and those cancel out. And so now here you can see, here's my A, here are my two B's, and then my products are E and F. Okay, so you can see there that that's how you're going to get the products if you only have the mechanism and you don't know for sure what it is. Now, this is what's going to happen if a simple collision isn't going to do it. These guys here, C and D, are called reaction intermediates. And they're only there for a certain amount of time until they turn around and then react with something else. They don't stay, they're not part of the initial reactants, but they're also not part of the final products. Now, usually what happens is that one of these steps is slower than the others, and so it becomes the rate determining step. Let me explain that concept this way. Let's say that you and a team of friends are getting together to make French toast with sliced peaches and cream on it for, I don't know, maybe a group of friends that you're having over. And so there are several different steps to the process. You are a baker and you love making homemade bread. And so you make homemade bread that you're then going to slice thick for your French toast. It's going to be somebody else's job to slice all the peaches. It's going to be somebody else's job to mix up the eggs and the milk and the cinnamon and whatever else you're going to dip that bread in to fry it. And then once there's somebody else's job to fry it. And then at the end, you're going to have somebody who's assembling the French toast and the peaches and the cream that you're going to pour on top. Am I making you hungry yet? So if you look at that, which step of that is going to take the longest? Well, the step where you're baking the bread is, because you've got to mix it up and you have to let it rise, and then you have to punch it down and you have to let it rise again, and then you have to put it in the oven and bake it. So obviously that step takes much longer than all the rest of them. So if that's the reaction we were looking at, then baking the bread would be the rate determining step. It's the slowest one. And until you've got the bread ready, it's going to slow everybody else down. Once your part's done, the rest of them are just going to click right along. Now, the rate determining step doesn't have to be the first one. It could be, but it doesn't have to be. Sometimes the rate determining step happens in the middle. I couldn't think of a really good example as far as food went where that would be the case. But rate determining steps don't have to be first. They just were in that example that I came up with. So let's say that in this mechanism that I've proposed here, let's say that this first step is the slow one, and then these two are the fast ones. So if I look at an energy graph of what that's going to look like, if I look at the amount of activation energy required for each step, what you can see is that here's the activation energy required for this first step. Here's the activation energy required for the second step. And then here's the amount of activation energy required for the third step. And you can see that this activation energy is much higher. Therefore, it's going to be the slowest, because I wrote that on the board down here in the corner the last time too, where I said a high activation energy generally is going to indicate a slow reaction. Okay, so this one is your rate determining step, RDS, rate determining step. And what's cool about knowing what the reaction mechanism is that you can find the rate constant if you know the reaction mechanism and you know which ones of these are going to be slow and which ones are going to be fast. Okay, so each one of these steps is called an elementary reaction, and in an elementary reaction only, the stoichiometric coefficients are going to be equal to that for the rate law. So for this particular equation, the rate is going to be determined by the rate determining step, which is the slow one. So it's going to be my rate constant times the concentration of A times the concentration of B. Okay, because that comes from the slow step. And because these are elementary, because these are the elementary steps, the stoichiometric coefficients will match. This is why a lot of times you're going to have a reaction where the rate law doesn't match the coefficients that are up here. You can see that it does match for A, but you can see that it does not match for B, and that's because only one of the B's is involved in the rate determining step. Okay, so if you have a reaction mechanism and you want to determine the rate law, all you have to do is look at the slow step and then use those stoichiometric coefficients in the rate law, and that's going to be the rate law for the whole thing. Okay, now that's easy enough if we have a reaction and a reaction mechanism like this one. But what happens if a different one is the slow step and I have maybe one of the reaction intermediates that ends up in that rate law? It becomes a little bit more complicated. And that's what example 11.6 looks like. Example 11.5 is a real simple one, which is similar to what I just worked through here, where all you have to do is look at the slow step, look at the stoichiometric coefficients, boom, there's your rate law. This one doesn't work that way. This one is on page 351. So if you want to look at that, but let me explain to you what you have to do in a situation like this one. Okay, so we are looking at this overall reaction, and these are the steps, the reaction mechanism for that reaction. You'll notice that I have two fast steps and one slow step. So this is the rate determining step. So if I write the rate determining, if you use the rate determining step to write the rate law, I'm going to get this. I'm going to get the rate equals the reaction constant times the concentration of N2O2 times the concentration of H2. Voila, I'm done, right? Actually, no, we have a big problem because you can't have a rate law that has things in it that aren't part of the reactants. The H2 is one of the reactants, but the N2O2 is not. So what do I do with that? I can't have a rate law that has something in it besides the two reactants that are listed. Well, if I look at the other things that are going on, I can see that this one is an equilibrium. And the equilibrium, I know how to write an equilibrium expression for. So for this one right here, because it's an equilibrium expression, I can write the equilibrium expression like this. I can say I have N2O2 on the top, and I have the concentration of NO squared on the bottom, okay? This right here is my issue, and so if I solve this for N2O2, I can then substitute what I get here into this expression. So if I say concentration of N2O2 equals K times NO squared, now I'm going to take this, and I'm going to do a substitution, okay? So that makes my new rate law equal to, here's my K, my N2O2, I'm going to put in K times NO squared, and then the rest of it is the concentration of H2, all right? This is a constant, this is a constant. I can combine them together into the same constant. I'm just going to mush all that into one constant. I'm not getting rid of it. It looks like I just erased it. I really didn't. I erased it, but I combined that number with this one. I could call it another letter if I wanted to, but it's just easier to call it K. And then now I have NO and I have H2, which are the reactants that I had to begin with. Now, is this an elementary reaction? We know it's not because all the reaction steps were listed, but what if I didn't know this? If you were just given this and this, could you say that's an elementary reaction? Well, you could say it's definitely not an elementary reaction because the exponents here do not match my stoichiometric coefficients, okay? If it was an elementary reaction, for sure, it would have to have a squared up here. Let's say that it did have a squared. Let's say that it worked out that way. Then would it be an elementary reaction? Not necessarily. Sometimes it works out so that your rate law has stoichiometric coefficients that match those of the reaction up here, but that doesn't mean it's elementary. That doesn't mean that it didn't actually have a bunch of steps. So be careful that you don't just automatically assume that a reaction that has a rate law that matches its coefficients with its stoichiometric coefficients, that doesn't necessarily mean it's elementary. It could, but it doesn't have to, okay? So you're going to get some practice now doing a lot of manipulation with these rate laws and with the reaction mechanism, figuring out how to figure out what that is based on the slow step.